Okay. How did the assignment go? Not too bad, but hopefully it introduces some questions for us as we start leading towards interprocess communication. We'll start talking about that some today. So the assignment, so I gave you an example of file IO. So kind of what was interesting here and why we were having issues at the end of class last time is there's kind of a generic OS level C library called open. And the open directory allows you to open files for read and write. fopen is kind of an abstraction that lays on top of open. It lets you work with these file structures, kind of, you can almost think of like an object type, except it's a struct type, making it a little bit friendlier, let's say, to work with files. But that comes with the side effect of opening a single file using fopen for both reading and writing won't work. So you can either go more generic or you can just do 2-pass. And since it wasn't something that we're focusing on, I just did it as 2-pass, where I opened it 2 different times. Open it for reading, get the value, open it for writing, write the value, so on and so forth. Make some sense? Or we could have used open and open it once and read from it and write to it. Doesn't necessarily matter. Okay, so the assignment was have 2 child processes, right? And have them, what are they doing? Counting up to 10. So effectively going back and forth with that file. So the file maybe starts off with a 0 in it. The first child process reads in from that file, gets the 0, writes back out the 1. The second child process then reads in the next value, writes back to 1, so it writes back to the 2, so on and so forth. Okay, so we're going to go ahead and kind of, I mean, most of you probably did this with a wait function, right? Just kind of timed it, like let's have things go to sleep enough often enough and kind of catch up. And that's what the intention was, kind of showing us that, okay, this is getting a little ridiculous, how much we're having to tell things to go to sleep, and almost like, hey, there's got to be a better way than this. So we'll go ahead and write this. So we're going to say for int I is equal to 0, I is less than 2, I plus plus, because we're going to create 2 child processes. The parent's going to do something twice, right? All right, so we're going to go ahead and say int PID. We'll go ahead and create our first child process. And then we're going to ask a question. We're going to say, if I'm the child, I'm going to do something. Now, if I'm the child, what am I going to do? I'm going to read in the value, increment it, write the answer back out. So I'm going to do this stuff. Okay, so child will immediately do this stuff and then go to sleep. Now, the child's going to keep doing this until they finally write back a 10, correct? Because we're going from 0 to 10. So we can go ahead and throw this inside of a while true. Do all this stuff. And then we'll just bust out later. All right, so if I'm the child, I'm going to go ahead and I'm going to just keep doing this forever. As of right now, just counting up, counting up, counting up. And we'll come back and add some more to this in a second. Otherwise, if I'm the parent, what am I going to do? I'm going to probably sleep for a little bit to get the next child offset, right? Because we're kind of playing with time here. So we'll go ahead and maybe say, let's have the parent go to sleep for, say, 3 seconds. Figure that's probably enough. You could probably do it in less than 3 seconds, but let's just say 3 seconds. All right, then the parent will spin back up. It'll create the second child. The second child will go and start reading and writing from that file as well. All right, but we want these children to be timed such that they are offset from the previous guy, right? So this first child will come through, open up the file, read in the number, displaying what the current number is right now. We don't have to have it do that, but we'll go ahead and have it do that. Incrementing it, close the file we just read, open the file for writing, print to the file the updated value, overwriting the contents of the file, and then close that file. And then we're going to tell this child to maybe go to sleep for 2 seconds. Okay, and we're going to do that over and over and over again. But we're going to say if and I'm actually going to move num outside of there. And we'll start num off at -1. We're going to say if num is equal to 10, we'll have this child go ahead and return. So this child will die off. Okay, as soon as he believes he has a number that's equal to 10. Now, this is going to get a little bit weird because now we're going to have 2 children. First child will read in a 0, write a 1. Second child will read in a 1, write a 2. First child will read in a 2, write a 3, so on and so forth. So eventually, one of them will have read in a 10, and the other one is I guess is done, right? So we could just say, you know what, why don't we just do this after the first read? It'll be an extra step through here, but after we go ahead and read in our value, if the value we read in was a 10, that means we're done. I don't have any more work to do. So we'll go ahead and just return. Otherwise, we'll spit out the number we just read in, increment it, and write it back out. And then tell this child to wait 2 seconds. All right. And this is all happening inside of, hey, I'm the child process. Parent's just going to wait 3 seconds. It'll do this a couple of different times. And then at the end, now we could tell the parent, I think you could say wait, is it wait null? I mean, typically, well, this will just be the, hey, you know, the bad version of this. So we're going to say we need 20 seconds. So we'll say 24 seconds here will be enough time to bridge. This program will run a little slow, but that's okay. Actually be more than that. I'll probably drop that down to 2 and drop this down to 1. Let's just call that good. And then we'll wait 20 seconds. And then the parent will finally die off. So we'll do like a printf, parent done. And then that program will end. What did I do? Oh, you could actually bring in I mean, while one true is I think it's an FC, just to show you, C. It's in one of the libraries. Just for future. Well, that's not the one I was thinking it was in. Let's just see if that's available in here. Nope, not in there. Oh, we also need to bring in the fork system call. So we'll say 1, and then fork system call is in unit. Blah, blah, blah. That guy. Yeah, we're not seeing the 10 because that parent or the child that they read it in, and before they spit it back out, they say, "Oh, it's a 10 die." So the child has now died, and we just waited for the parent to finish. This guy should have a 10 sitting in there. All right, so we had the 2 children do that, right? All right, so that would be a reasonable solution to the homework. So questions about that. Hopefully we're kind of feeling like, okay, this just can't be what systems programming is like with all the sleeping and things like that. Go ahead. Memory address of what? You mean the process IDs?
Yeah. Or because like the process ID is 0 for the children, right?
No, not if we do get PID.
Oh, yeah.
So you want to say next to the value is
Yeah.
percent %D. I think it's just that. Oh, this is going to go from 10 to give me a moment because it died right off the bat because they both read in a 10 instantly. Said we're done. So we'll put it back to it. Oh, see, interesting. The with the sleeps, we have them too close together right now. So the same child did the first 2 counts. Then we were alternating okay. So we probably do need to put a bigger gap in there. Why are we getting an initial? See, the read for the second one is happening before the write. So whenever we're printing it out, that's immediately following the read. Which is this guy right here. We open it, we read from it, we print it out. Let's just make it a little bit obscene. And then let's actually, you know what? This is probably not the problem. We're probably getting the second child started too quickly. Actually, that's guaranteed to have the first child do it twice. Yeah. No, this seems to, we've got a reasonable cadence now where they are alternating between each other. But same difference, this is clearly not the way programming should work, where we're just hoping that whatever you're trying to do happens inside of a certain period of time. Yeah. seems very slow and not very fast. Sure. And you know, we could effectively, we basically just did this exercise where we were kind of playing with the timers, right? You've maybe heard me mention this in another class, another alternative. So actually, we would call this the upgraded function, sleep, because in older programming, something that programmers would do is they would have busy wait loops. So they would write like a for loop that is, so instead of sleeping for 4 seconds here, they would say something like for int I is equal to 0. Actually, we'll have to do like a j. J is less than, I don't know, 1,000,000. J plus plus, something like that. Literally just have it do something 1,000,000 times. Hopefully that's long enough to be 4 seconds-ish. All right, something like that. Chances are the compiler is going to just ignore this because we're not doing anything inside the body. So actually, let's just see that real quick. Yeah, just all got done. We should be able to. I'll just put something random inside the body of this guy. We will say int count is equal to 0. We'll say something like count plus plus. So for 1,000,000 times, we'll just increment count. Yep, not enough. Got to keep adding zeros. Oh, no, it's not. It's still a 10 at the beginning. And not enough. Computers are getting fast. We'll double up there. Oh yeah. All right, so this would be, it actually feels like about 4 seconds. We hit the sweet spot. Now, we would say this is definitely worse, right? At least the sleep said, look, you're going to sleep for exactly 2 seconds. However you're going to accomplish that, that's fine. But that's how long you're sleeping. It's for 2 seconds. All right. Where this guy is, how long is that code going to take to run? So right now, it's taking about 4 seconds on whatever operating system and hardware setup online GDB is using, right? And but as those computers get faster, it's going to count through that stuff more quickly. 100%. And I had this issue, and if you've heard me tell this story before, it's not going to be long, but there was a game in the arcade when I was a kid called Double Dragon. And it finally came to PC. I think we were running DOS 3 at the time. And when we first got the game, it was great. It's like, oh my gosh, we're playing this game. It was only in the arcades. It was awesome. Several years later, we installed it on our IBM 486 DX2 66 megahertz computer, which sounds like a toy by today's standards, but was way faster than the computer that we had, because originally Double Dragon was running on our Epson. Epson used to make computers. So we had an Epson computer. It was an x86, I don't know, probably 12 megahertz or something like that. So anyways, the new computer was way, way, way faster. And it was evident that they did all their delays, like when does the next monster come out, based on busy wait loops. Those levels got way harder because as soon as the level started, everyone was there. End boss, they were all just on top of you, just killing. So that was a childhood experience with bad programming. That's the idea here. So we would certainly say this is bad practice. But what is interesting here is if I take that out and we take this out, I expect this This will be an interesting little experiment. I expect it to not run as it intended there. Oh, it still did. Oh, maybe. It's a good.
Because when you just entered there, it wasn't working.
Well,
It was a lot
well, yeah, I had less zeros and oh, it's still running. Missed the counter, but it's clearly delayed. Because what I was expecting to happen is one of the jobs of a compiler is to make a bad programmer look like a better programmer. So one possibility here was, is as it looked at this code and you're doing something and it saw there was no body to this loop, maybe it would be difficult for it to unravel the Boolean expression here to figure out, is this like I'm waiting for any key to be pressed where it would be reasonable to just kind of wait. And we could actually do it that way too, right? You could have done like a read something in from the user here. And that way we have to just keep pressing the space bar to get the children to alternate. That it would work. So then you wouldn't need the timers. Your program would finish quicker. But in any case, I kind of expected maybe it would say, look, this is a waste of time. We're not going to put that in the executable code. But it didn't go so deep into the Boolean expression to determine that was just math. All right, so in any case, a busy wait loop we're going to say is a bad idea. Similarly, we'll say just putting a sleep timer in there is better than the busy wait loop because at least we're controlling time. Time isn't shifting greatly, but this is still a problem. So we need to have a better solution for this. So, you know, as you said, we're not going, it needs to be fast, not slow. I think that's what he said, right? Yeah, Jason said computers are usually fast. Yeah, it was really a bad way of saying it.
I have a little
Oh, better than that?
Yeah.
Okay, go ahead.
You just have a computer console like what 100 billion seconds over and over again.
Mhm.
So this program uses 2 processes to count to 10 in 30 seconds.
Yeah.
Pretty slow.
That's true. You could also say it's not fast.
It's not fast.
both of those things are truths. and it's slow. All right. So put ourselves in the shoes of a programmer, you know, back in the day. So we're a little bit past the double dragon busy wait loop days. Like, okay, busy wait loops obviously stupid. So we'll just put little sleep timers in here because that's what's in our toolbox, right? Sleep timers. So now, given what you know right now, what kinds of things could we do to try to make this fast and not slow at the same time? What kind of things can we do to make this, as he said, fast and not slow, while still not relying on these sleep timers? Any ideas? Clearly, we're moving in the direction of inter-process communication, but we're going to put ourselves in the realm of, hey, we're hackers. And we have these tools in our toolbox here. What can we maybe do to kind of solve this? What do you think? Or did any of you, hopefully some of you tried some stuff on the assignment. Go ahead. Okay, so we could do that. We could, that would require the children to know about each other one way or another, right? But the good news is the parent knows about the child. So the parent can get, the parent can set a variable for the child. And maybe since we know there's 2 children, one of the children can say, okay, well, if this variable is equal to something other than -1, I'm the other child, and I'm waiting on that dude. Something along those lines. So if we did give it to both of them, that would be possible. I'm trying to think, can we actually get both process IDs? Because if we're going to have the child waiting for the other child, so we have two children, each of them have process IDs. We can certainly let the first child, both children can know about the parent. But can the second child know the process ID of the first child? Because it's not the first child that's spawning the second child. So I don't think we can, with what we know right now, I don't think there's a way for us to directly do this. We could probably do something with, we've seen it in the slides already, calling like that PS, the list, the thing that lists all currently running processes. So maybe something like that, that lists all of our current running processes and look at what the name of the process is. And if the name of the process is main.o, you know, the executable that's running or something like that, then we'll assume, oh, that's one of the kids. And if it's not my process ID, it must be the other dude's. We might be able to Sherlock Holmes it and get that process ID, but it certainly wouldn't be convenient. But not a bad thought. If the children could just say, hey, I'm going to wait for the other guy, you know, we could kind of time this. What else? Go ahead. The parent could create that. It actually probably does. There's probably a way of, because I think I said it earlier, I think you can say, I'll just try putting it in here. I think wait null. I think that says wait for all of my children to die. I get what you're saying. So the point is if this works, then the answer would be one way or another, it has access to all the child PIDs automatically without us doing anything. Hold on. What's it in, sis? Okay. So now when we hit the 10, presumably the parent will immediately die. We won't have any extra waiting. Yeah. So that tells us through investigation that if this works and this parent somehow is able to, possibly through a system call, you know, is able to get the process IDs of all of its children. Now, the parent could also collect those process IDs, right? Because if we're in this else, so if I'm the child, I can get my process ID by saying, hey, what's my process ID? But if I'm the parent, PID will hold the process ID of the child you just created. Does that make sense? So we could do, you know, give ourselves a an array. So maybe we do a int kids 2, something like that. And then we say int kid count starts off at 0. So then if we're the parent here, we can go ahead and do something like kids at bucket kid count is equal to PID kid count plus plus. Now, when the parent was done doing their thing, we could then say, wait for kids at bucket 0, wait for kids at bucket 1. I don't know if it's just wait or wait PID. I think it's just wait. So maybe it is wait PID. Yeah, because that's doing for a location. Might be wait underscore PID. What was the name of the function you used? Oh, you did that?
Yeah.
PID is an int. So that does take a location. I think we saw that a second ago. So if I take that back out, we'll see the error message that we got. Yeah, it requires the location of the number, not the number itself. So that's why it worked. So this is a number that lives at that address. That lives at that address. Okay, so we could do that. Or wait null just says wait for all my kids. That optimizes it a little bit, I guess. So at least we're finishing as the parent dies as soon as all of the children are done. Go ahead.
So if you have this wait for safety for any one of that people, so it's not-
But what does wait do? Wait waits for a process to complete, not to finish one pass through the loop. But I mean, it's a good thought. I mean, this is the kind of the direction we want to be thinking, right? You know, somehow we want the children to kind of synchronize with each other, you know, so that they're, you know, doing part of the work, the next part of the work, the next part of the work, so on and so forth. Okay, other approaches. We're kind of seeing where are the fence posts. We know we can have variables, but they don't share the variables. They get their own space. We saw that last time. Go ahead. Signals, okay. So now we're starting to get into some of the inter-process communication stuff. Because one thing I want to make a differentiation, and you wrote a paper on this. I want to get a slide in here about it. Processes and threads solve similar problems, but are not the same thing. We're going to see. I might show it today, but I don't want to go down. I don't want to switch to threads quite yet. But for instance, there's this thing called the semaphore. It's based on something called mutual exclusion. So a semaphore is the big brother of something called a mutex, M-U-T-E-X, which says we want to control access to this resource. And the thing is, semaphores work very conveniently with threads because of the nature of threads. Threads share the same memory space as the parent. But we saw last time that processes get a copy of their own memory space. So all of a sudden, even though things look like they should know about each other, they're actually going through a different bouncer, a different control structure. There's ways around it, but until we get into threads, threads solve a lot of these problems for us. Not that they will automatically synchronize, but we have a lot cleaner communication between threads than we have with processes. Partly because the processes, because they live in completely separate memory space, are reliant on using operating system level things for talking to each other. All right, so you talked about signals. What did you find out about signals? Okay, so think about what we're trying to solve. We're trying to solve something very similar to real life. Okay, so if you and I are working on doing this counting thing, right? I read from the file, I increment the value, I write it back, and then I wave a flag, right? And then you know, okay, it's my turn. And I'm sitting here waiting for you to wave your flag. You do your thing. We're signaling each other, and we have our game plan. We're going back and forth, right? Okay, that's what signals effectively are. We have functions that allow us to do that. But what had to happen? What we're trying to solve a problem very similar to a solution in real life with a signal. Not only did I have to raise a signal, you had to know to look for it, right? Otherwise, I'm just the one sitting there waving the flag, and people are coming up and giving me coins in my tip jar and pat me on my head, that kind of stuff. You have to know to wait for me to give that signal. You need to know what signal to wait for. And we can have different kinds of signals, right? You think about the people who control aircraft, right? When they're trying to park a plane, they have the flashlights with there's different little moves they're doing, and not all those moves mean the same thing, right? So there's multiple signals that those pilots are looking for. So that's one thing we could do, is since these two children could be looking for a signal, and maybe the second child waits for a signal to show up, that would be a possible solution. I think that's represented in this little picture here. You don't like this picture? Hi. Really?
Yeah, although yeah, the lighter colored.
So you want me to get rid of the picture? Well, you don't like the picture. It doesn't have signals on it anyway. I took the picture from a website. It's not like a. So here's this guy. So actually, I'm going to do something here, just so we'll look at signals. All right, so as I mentioned, we could have different color flags, right? So a signal is just a number. All right, now built in, these are kind of normal common naming conventions for signals, but all we're doing is defining a constant here. That's all these guys are. But these are different color flags. You can think of it like that: signal 1, signal 2. So maybe you and I are waiting for the signal 1, signal 2 type thing. I raise signal 1 when it's your turn, you raise signal 2 when it's my turn, back and forth, back and forth. Okay, now one thing we do need to work with, and we'll get into maybe some more of the details, but the operating system. So again, we're having to go outside of the processes here. When a process needs to talk to another process, we're reliant on working through entities that know about both processes. And at the very least, we know that the operating system knows about both processes, correct? Who else knows about both of these processes in our current example? The operating system is kind of the easy catch-all, right? OS knows all as far as what's running on the computer. So a child process can say, hey, OS, raise this signal, and whoever else is looking for it is gonna get that signal. Now, we do need to be a little careful with that, because if you're raising that signal and you're picking kind of a generic number, You know, maybe like these guys probably come from some sort of standard like you know, SIGINT, interrupt a process. You know, maybe you're waiting for me to raise the number 2, but how many other processes are on the computer possibly waiting for that same signal? So we need to have unique signals that we think only you and I are sharing, because we're working with a global entity here to process our signals, for us to say, hey, raise this flag, and any process that sees it and is interested in that signal might respond to it. All right, so let's see, they give us a handler for it. That's just the default handler that comes with signal.h. So inside of, so SIGINT, look up here. This guy is the interrupt a process. So really SIGQUIT would tell the process to immediately end. Built into signal.h, we have default handlers for those. So for instance, to interrupt this process, there is a handle SIGINT that will tell the processor, or tell the operating system to interrupt this particular process. Forever, well, they're going to print hello world, then we'll sleep, spin back up, so that we just say hello world, hello world, hello world. We're only sleeping for 1 second. Eventually, it's going to terminate as the result of how handle SIGINT is working. But I want to get 2 different processes talking to each other. All right, this one might not be a bad one to look at. Bring this into my code here. I'm just going to create, stop that. I'm going to create a new project, but I won't save it, just for us to explore this stuff. All right, so I've written my own signal handler now. So handle SIGINT, I can name it whatever I want, because when I raise the signal, I tell it what function to call. Okay, but I wrote my own. All right, so this guy gets in the signal, and we're just going to say caught whatever signal was passed in. We're not dealing with kids or anything yet. We'll add those in here in a second. So we're going to go ahead and signal. So I'm going to raise the flag if I'm the parent in this case, and then we're going to sit here and, you know, spin forever is what this guy's going to do. Get the caught signal. I'm going to put a sleep in. I bet you this is. Signal handler not part of that. Let me call it something other than handle SIGINT. Maybe that's being protected. It's not. Kill is the default way to send signals, but this should allow us to raise a signal. to not know about, well, SIGINT should be part of signal. But this is just a number. So I can come in here and I can say 2002. Give it the PID and then the signal. Blocking signals. So that might be a problem with online GDB. Did you test out signals on online GDB? Yeah. So it will be unfortunate. Let me just test this real quick. So this blocks it too. So it's not an online GDB thing. Let's call it unimportant for right now. I'll figure out how it wants to do the signals. That way we can finish talking about the. Oh, actually, I don't know if you noticed that there at the end. It did. Actually did catch it. I don't know if we have a way of mimicking that. So it's sitting there and waiting. So now when I say Control C here, which sends a SIGINT, then I got the caught signal from this guy. And that's because I used a one of the default signals of the operating system, which is SIG interrupt, which then also means that because I chose this program to handle that for me, I no longer can kill this program with a Control C. I probably would just need to do a reset or something like that up here. Or maybe just kill it. Kill it. So this guy, the signal registers this handler for a signal like this. Kill is how we raise a signal. But we tried to do the raise. We'll come back to it. So I can finish talking about the other inter-process communications. All right, but we see the problem that guy's trying to solve, the signal problem, where we can raise a flag, somebody else could be looking for the flag, things like that. All right. Now, in real life, here, without going on to that slide, in real life, ways to solve the process communication problem. So one thing we looked at here is signals. All right. In real life, you have two people who want to communicate something to each other. Okay, one thing is we could do kind of silent communication, raising the flags. What's another way you might communicate with another person to synchronize, the solution to some problem? So we can think of signals as, old school raising flags or something, but we could also think of like texting. You send a message that says go. How else might you communicate with somebody else? Go ahead. Okay, so call them, right? So we're sitting here talking to each other directly. That means we're kind of in the same room or something, but the idea is like the two of us are in isolation, right? We don't see each other. We have no way of directly talking to each other. But if there is somebody who knows both of us, in this case, the operating system, we can go through the operating system to talk to the various endpoints, right? So we can tell the operating system to raise the signal. Somebody else could be looking for a signal with the operating system and have a handler for that. And I'll give you an example with two children. I'll write that up before Tuesday. Similarly, we can open up a communication channel with them, and that's through something called a pipe. Now, some of you have probably, well, here, I'll show you let's see what they say. So communication between two related process, half duplex method. So anybody know what half duplex means? Half duplex means communication in both directions, but only one direction at a time. That's how a pipe works. Okay, so if I'm sending you a message, you can't be sending me a message at the same time, which is maybe kind of good in this case, because the idea is that you're going to be waiting to hear a message, maybe yell into the walkie-talkie, so something like that. But I'm not limited to the messages I'm sending. I can send you whatever data I want over a pipe. I can feed you all the bytes of a JPEG if I want to. All right. So first process communicates with the second process. In order to achieve full duplex, another pipe is needed. Okay, so if we want to have real-time communication in both directions, you have to open up a pipe to me, I open up a pipe to you, and then we just kind of have a circular communication. Some of you have probably heard of something called a socket. Okay, any of you heard of sockets before when it comes to computers? Probably in the context of networking. So when we talk about opening up a socket, sockets are effectively pipes, but across a network. So instead of talking to another process on the same computer, you can open up a socket to a different IP address and talk to a running process on a different computer. But they kind of are solving a very similar problem. It just lets you leave town. Long distance phone call, if you will. Okay. And nothing actually prevents you from opening up a socket connection to the current computer. Current computer is called localhost. And from a networking perspective, works, we'll call this similar to a pipe if used on localhost or 127.0.0.1, which is what's called the loopback device. So the home IP address of any computer is 127.0.0.1. That makes it compatible with a network lookup, IP compatible. But whenever you say 127.0.0.1, it loops back to the current computer, right? And you may be seeing the geek shirts that say there's no place like 127.0.0.1. So there's no place like home, but only if you know what that means. Yeah. So in any case, a socket is not identical to a pipe because sockets are actually full duplex. You don't have to open it. They have a two-way stream with sockets, but they do solve a similar problem, communication, and nothing actually keeps you from opening up a socket to localhost. Sockets listen on a certain port on the computer. So we can have a child could open up, they can say, I'm going to listen on port 7575. And so the two children agree on that channel. And then they both open up a socket connection on that channel, localhost port 7575. And then they can talk to each other, and we can invent our own little, made up language for when it's whose turn it is, right? We can decide to, think about this as solving the problem in real life. We each have a walkie-talkie. We've established a communication channel between each other. And now we invent our own little language for deciding whose turn it is. All right. So sockets give us that flexibility. Signals are limited in the types of messages you can send because you're just kind of, raising the flag, shooting a flare into the sky, that type of thing. You know, you're not sending a whole bunch of information along with that, but it still lets somebody else know about it. Okay, so we have the idea of a pipe. All right, how else might you communicate with another person in real life? We're not even talking about computers anymore. We're making the assumption that there's probably going to be an inter-process communication equivalent to things that already exist in real life. Okay, so you and I are trying to synchronize on something. We got pipes, we got signals. What else? They're passing a note. Okay, well, it would probably, so it would be a pipe or a socket if we gave the note directly to each other. But a note would have more data on it, right? You know, you're not limited to just, you know, red flag, yellow flag, whatever, just some number, you know, so you can, you know, write a whole bunch of stuff on the note. And if I hand it directly to you, that would probably be something that goes over a pipe or a socket. But what else? Okay, but that's slower direct communication. You know, we're relying on the post office to be the operating system, and they're going to deliver that message to you just a little bit slower. Okay, kind of think about like espionage, spies. How do spies communicate with each other from the movies? Go ahead. They do what? Okay. Oh, actually, that's not where I was going next, but that's true. And we have an equivalent for that. Okay, so putting messages in some agreed upon place, right? So if you want to take the you know, kind of a starter version of that, we have like a drop location, right? You know, to check you know, under some rock by you know, the water fountain you know, by 3 p.m. every single day. And if I want to get something to you, I make sure I get it under that rock before 3 p.m. So we have an agreed upon place that you're going to check at some sort of cadence, right? Okay. So we have this idea of message passing. All right. And along with message queues. So message passing, this one would be similar to the drop location, where they have to check for their messages, kind of like calling into the answering machine, that type of stuff, where the message queues is going to work similar to kind of what you're talking, except, you know, less hidden messages than a newspaper and more of, look, here's a bulletin board that lives in the operating system that you could just post stuff to that different processes might be interested in, and they can come check it when they want to check it. Okay. Probably shared memory is the thing most similar to the drop location. All right, so shared memory. This is the idea of having a place in memory that we both know about, that we've agreed upon, that we're going to put stuff. Okay, like the rock next to the fountain. All right, and the two sides will alternate. Well, we can decide how we want to use this shared memory, but this would allow us to have memory shared between two processes. Because right now, even if we we saw last time, we create a pointer. As soon as we create two child processes, they get their own local pointer for that address. Things that you write to this pointer aren't readable from this child over here. Those are two separate memory addresses because those memory addresses are enclosed within the process space given by the operating system. Okay, so even though we generated memory and it might even have the same memory address, we saw that last time, we aren't actually able to write stuff to that memory location and read it from the other guy. It's a different memory location, even though it looks the same. So the operating system provides a way of creating a global memory location that both children would have access to. Okay, because they're not looking locally for a variable, they have to attach to a global shared memory. So the operating system is providing that service to our processes. So a portion of memory that the OS provides on demand that is accessible by all processes, we're going to say in the know. We typically name the place in shared memory. So as long as you know the name to it, the name of it, there's some more secure shared memory options, but as long as you know the name, kind of like the password, you can get to you attach that shared memory. Now you can read and write from it, but we would still have to develop a cadence for communicating. So this is like that rock next to the water fountain. We would have to decide, if you're checking for messages, how often do you check for messages? Because at some point you might check for a message and you don't get it, but maybe as soon as you leave, I actually put a message there. So we'd have to have some pre-arrangement for how often you're going to check that drop location. All right. FIFOs are kind of like pipes. Message queues are like that. Yeah, that's probably good for that stuff. All right. So realistically, these are probably our three go-tos. I'm going to put socket here. So we're going to say a pipe is a one-way communication channel between two processes and is managed by the OS. So we're going to see that as a pattern. It's the OS that knows about the multiple processes. So they would be the ones that can connect this communication channel between those two processes. But it is a one-way communication. So each process would have to set up their own thing. A signal is provided by the OS to allow processes to raise signals through the kill command, which is a little bit misleading because typically when you think about kill, the kill command is usually meant to kill off a process. That's just the default signal. You can give it a different signal instead of so I think there's two versions of kill. There's kill with just a process ID, and there's a kill with a signal and a process ID, which would send a different signal up. Signals through the kill command, or listen for signals by registering a handler for a particular signal. So an individual process could register multiple handlers. They could say, for signal 3, I want to do this. For signal 4, I want to do this, that kind of stuff. They could also have a single handler that all of their signals get registered with, but the signal handler itself gets whatever signal it got, was sent to it. So we could say, oh, if the signal you sent me was this, do this stuff. Else, do this other stuff. Something like that. So you can either call multiple functions depending on the signal, or you can have them call a single function and then have if statements in there to determine which signal did you actually get. All right. So all of these are in the context of processes, not threads. Threads make life a little bit easier because you are now moving down a level where who knows about all the threads? The parent process. Does that make sense? Now, thinking about these for a second, though, if we go back to our example from today with the counting, the parent, in the last example we wrote, we stored the process IDs of the kids, right? The parent knows about all the kids. Do the kids know who their parent is? We have a function called get PPID, get the parent process ID. So a child process can determine who their parent is. So we spawned off two child processes. Both of them can ask, who is my parent? Now, given the process ID of their parent, they could perhaps open up a communication channel to the parent and have the parent maybe send the process ID of the child, the other child, something like that. So you could, one way or another, get some information back to the child about the other child. That makes some sense. So you can kind of play with these ideas similar to what we might do in real life, you know, with our various mechanisms for communicating. Now, if we take a step further back and we go back to the early days of the operating systems, that maybe we're starting to add some of these more generic solutions to problems. The assignment for today was specifically looking at files. And one of the services provided by the operating system is a file system. So might communicating with files be a fairly common thing that happens on a computer? Okay. So might there be a special mechanism specifically for governing access to files that isn't as generic as these other things we just talked about at the high level? So we have something called file locking. So there is a mechanism based in, well, there's the C operating system calls called file locking that allows you to effectively set the permission of a file to locked while one process is doing something with it, and then unlock it when you're done with it. And the other process wouldn't be able to even open that file until the lock was removed. That makes sense? All right, so file locking is specific to files where a file can be locked for read, write, or both. And other processes are blocked from accessing that file until the lock is removed. So file locking would be the file specific type of interprocess communication. Would it fall underneath interprocess communication? Probably not. It would fall underneath the idea of mutual exclusion, mutex, because you really aren't communicating between these processes. You know, they don't know anything about each other. You just know that, hey, you try to open the file and it won't open. What do you say? You're like, well, somebody must be locking it. I don't know who. Somebody. So we are providing mutually exclusive access to a resource. So we're going to call this provides mutually exclusive. I'm going to put in here that guy because that's a word you're going to see pretty often, mutex, to a file. Okay, so the idea of file locking is we effectively put a bouncer around a file. The upgrade to that guy, we have something called a semaphore. This provides mutually exclusive access I'm going to call it provides flexible mutually exclusive access to a resource, which could be a file. Okay, because now what you're doing if you're using a semaphore is you're not actually locking the file. you're just making anybody who's going to use that resource, which might be a file, they have to go through the Semaphore in order to get access to it. The Semaphore and the file actually have nothing to do with each other. You and I have just decided that we don't grab the file directly. We check with the bouncer first to see if it's available. So we've agreed upon using the Semaphore to control access to something. So Semaphores end up being more flexible in that they'll allow us to protect any resource as opposed to just the file with file locking. One issue though, and we'll explore this when we talk about Semaphores and look at code examples, is Semaphores work very well with threads, have issues with processes because of the nature of creating the Semaphore. There's two flavors of Semaphores. There's counting Semaphores and there's binary Semaphores, and there's ways around it, but they behave better with threads. But we will look at that. Okay, so questions, comments, concerns, bribes, about any of the stuff we talked about. We're all in agreement that sleeping to wait for things is not the greatest idea in the world. Okay, we'll come back on Tuesday and we'll look at a couple of, I'll get a working code example for a signal, and then we'll try to write this from a signal perspective to see if we can get it faster or not slow. And, and we'll see how that goes.